So there's a whole lot of stuff going on here. So let's talk through all the individual pieces. And then from there, we'll actually do some testing. So the first piece here is, of course, the 1702 EPROM programmer, the S100 card. This is the programming socket. Pin 1 is in this corner up here. There's a strap down here that will enable the high voltage without the software telling it to be enabled. So the system works by enabling the high voltage, programming the byte, and disabling it. Receives the next byte to program, enables the high voltage, and disables it. This jumper will force the high voltage to be on so I can measure it down here to make sure the voltage rails are correct. There is a 50-volt transformer sitting back here that's passing 50 volts AC in through here, gets rectified, filtered, and then gets voltage regulated down to this plus 47 and plus 59 volt supplies here. And then those voltages are passed through the transistors down here to the socket. There's two P8212s here. Each one of these is an 8-bit latch. They're a very old school 8-bit latch. I used as, this is based on a design from 1976, the programming piece, and it's true to that design, including the old parts that it uses. There's some 74 LS 160 and 161 counter logic down here that produces all the various pulses to program the part. There's, of course, my RC2014 sitting over here. It's strapped to the fastest clocks for both, clock 1 and clock 2. The baud rate is 115K going to the computer off of the FTDI cable here. It's just a, it's a standard. There's a compact flash card here with a CPM on it. It's a core basic CPM build. There's an interface card sitting here that has all of the address and control signals pretty much from the bus down low. I've got A0 through A7 brought along and jumpered to A8 to A15 on the S connector here, or the edge connector, and we'll talk about that. And then data 0 to data 7 come through to data 0 and data 7 out and in both. Now let's talk a bit about this. This is the S100 or MSI Altair S1 bus configuration. This isn't an IEEE 696. The original MSI and Altair used the MSI bus, which was an earlier version of the bus. Later on, the bus became the IEEE 696 and was greatly extended. So what happens on this bus is, of course, A0 to A15 come directly in on it. They are decoded down here. So the board looks to decode 8 ports, of which 4 are used. So the high order addresses are set here, and right now they're all set to 0. So the board is sitting on port 0 through 7. Port 0, as it says here in the documentation, latches the data to be programmed. Port then, plus 1, so port 1 latches the address. Writing to port 2 tells it to generate the programming pulse, and there's an LED here you'll see flash when it programs. And then port 3 read allows me to read the status of the programming logic, so I know it's busy, because it takes about a second to actually program a byte. So like I say, it's strapped to port 0. The A7, 6, 5, 4, and 3 can be put any place in the memory space. 0 works based on the card configuration here. So that's what I'm using. The S100 card definition here has 8 pins that are data. This is always hard to describe. So thinking about the 8080 processor, the 8080 processor can receive data. It can have data coming in. And so that becomes the DI0 to DI7 pins here. So when the 8080 processor wants to read, it reads off 8 pins on the bus here, that data into the processor. When it wants to output or data out from the processor, there's 8 different pins the data comes out on. So the data into the processor and the data out from the processor are separate sets of pins. And what I've done here is there's 2 red wires here. You just can't see the bottom one. There's 2 orange and 2 yellow in the stack. And I believe the top row of here goes to the data in, and the bottom row that you kind of can't see goes to the data out. That could be reversed. It doesn't really matter. On the 8080, and that's why this card's designed the way it is, on a port operation, the port number is put out on A0 to A7 and then duplicated on A8 to A15. So the board here was designed, for whatever reason, to use A8 to A15 to decode the port address. The Z80 works differently. I believe the Z80 puts the port number out on A0 to A7, puts the data out on D0 to D7, and I believe it replicates the data on A8 to A15. I could be wrong. So I've ended up taking A0 to A7 and bringing those around to A8 to A15 because A15 is what the card is monitoring to figure out what port it's talking to. I'm powering the board for 5 volts directly off the 2.5 amp 5 volt connection I've got here. So there's a couple of leads bringing in +5, a couple of leads bringing in ground. The 5 volt logic on the board draws about 1/4 amp in operation. So the power supply is plenty robust enough to handle it. There's a voltmeter sitting over here we're going to use in a minute. There is my model 763 1702 programmer. It's a manual programmer. You set the data to be programmed on the switches. This programmer's odd, and then it was meant for an alarm system, and it programs 16 bits at a time. So it would program address 0 and 80 hex here, and then address 1 and 81 hex here, and then address 2 and 82 hex here. So you've got to put in 16 bits at a time, and it does that weird offset, and it's really difficult to get everything correct here to program. And I've also got an issue where the sense amp or something on this LED doesn't always work, and so it doesn't always show a 1 when it's supposed to. It's just a pain. But in read mode here, I can reset the address and I can just step through the part, and I can see down here on the displays what's coming out of the part. So a 1702 erased, we'll pull one here. I have this many 1702s to work with at this point. I don't have a lot. We'll drop in a part that's erased. The addresses are reset, and as I step through it, as I step through it, you'll see all zeros, and that's correct. The 1702 erases to all zeros, where later generation EPROMs erase to all ones, 1702s erase to all zeros. And yes, my putting the part in and out of the socket live here is the correct procedure. There's no power switch on this guy, and it literally says on the label to not put not have a part in the socket when you plug it in. So it is in the end how it works. I suspect that voltmeter is shifted. It hasn't, and you can't read it, but it hasn't shifted. So I'm going to do a first test here. The 5 volts is live. I've got the jumper on that says enable the high voltage. I want to look at the 47 volt rail here on the meter and make sure we have 47 volts. I'm about to plug this transformer in. It's plugged in, and we're seeing 47 volts, so it's got good regulation. There should be 59 volts here. Let me plug the transformer back in, and we see 59.1 volts, so I'm absolutely fine. There is a voltage adjustment potentiometer here that sets those high voltages. It's still in calibration from the last time I used it. Now I'm going to remove this jumper, and I'm going to move it just off by a pin. So the 2 pins are now open, and that will disable high voltage. So if I get on the rail here now and I plug in the transformer, there'll be no voltage there. It's disabled at this point. Like I say, the programmer will enable the high voltage when it needs to. I'm going to go ahead and remove these. Well, I don't know if the meter will be quick enough to capture it or not. We'll leave the meter there. It might actually show the high voltage come up and go down. I don't know. I've got a basic program in MBasic, so CPM is running MBasic, and I've got a little simple basic program that at address 0 will write a hex 1, at address 1 it'll write a hex 2, at address 2 it'll write a hex 4, at address 3 it'll write a hex 8, then a 10204080, and then finally at address 8 it'll write FF. So it's only going to program the first, what is that, 9 bytes of the device. And it's going to give us a running bit pattern that'll be bit 0, bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, bit 7, and then an FF. That's what should happen here. I couldn't remember for sure the device orientation. I thought pin 1 was in this corner here, and it is. So I'm going to drop a 1702 in. I'm going to close the socket. I'm going to go ahead and plug the high voltage in. I'm going to type run here on the keyboard. I'm not going to press run yet. So what you should see happen here when I run is this LED right here, this red LED, which hopefully is on camera. It just barely is. Let me move this lead out of the way. You should see a red LED down here. Boy, it's hard to point at. Down here, flash. So hopefully you'll see the red LED flash basically 9 times here. So high voltage is there. At least we're plugged in. Let me go ahead and hit enter. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's the 9 bytes written. High voltage. I have no idea if it did something on the meter or not. I wasn't watching. Let's Let's go ahead and pull the part out. Drop it in the socket here. So the sense amp here is giving us trouble. So it's not reading a 1 here when it should be. But if I step, so this address count here is in decimal. So there's address 1, 2, 4, 8, 16, 32, and well, I counted that wrong. Let's go ahead and reset. Let me count through that right. There is a 1 here, I believe. We just can't see it because the doesn't want to work. That should be hex 01, hex 02, hex 04, hex 10, hex 20, hex 40, hex... Let's reset it again so I can get it correct. Hex 01, 02, 04, 08, 10, 20, 40, 80, and this next byte should be an FF. And again, I suspect that's just that byte not being happy there, or that bit, and I don't know why. Usually it flickers. I can't even get it to flicker here. Now, in playing with this before, it looked like making a couple of programming passes actually made more sense. Properly programming a 1702A is typically you make a program pass with there's some parameters, pulse widths and things to it, and then you read it. And you try it multiple times until you get the part programmed. And then I believe you program it 30 more passes. There's a weird algorithm to this, that because this is a write only, it's a program only board, we can't implement that read logic. That's why I have standalone reader over here. But I'm going to go ahead and make a second pass on it. Hopefully you can see the LED blinking, and that just programmed the same bit pattern in. Just drop it back in the socket here. We actually saw, I wish that wasn't floating. We actually see some LEDs flash when I close it, as the part gets powered up. And it really just isn't going to show us anything there. That's kind of sucky. Let's pull the part out. I don't really want to try to program any of the others at this point. Oh, that blows that either that's finally failed, or it's the reason I'm not using this to manually program is A, it's really difficult to do and get right. Partly because the display here is decimal, so H is actually address 0, and then as I increment, you'll see it go to address 1, 2, 3, 4. Like I say, it's in decimal. And so it just gets really confusing. I'm working in octal or hex down here. I'm reading in decimal. Like I said, this was designed for an alarm system. And although I've programmed stuff on it, like I say, it's just a pain. I do have my retro chip tester that I will be putting the program parts back into and getting dumps of those that I can then compare against the pattern. But I think that really walks us through the hardware. Actually, I'm going to throw one more pass on him. I want to watch the voltmeter. I haven't actually watched the voltmeter yet myself to see if it actually reacts. So that obviously wasn't correct. I think it's just because it's pulsating. It's pulsating so quick that it's seeing an average, I guess, of 9 or 8 volts. So kind of a worthless test. Yeah, that's just a pain. If I, at this point, well, I'm not going to reach in there. There's 80 or 90 volts across this cap, and it'll bite you. It's a nice DC voltage. It will bite you. It's bit me a couple of times. Just one last thing to mention is there is onboard regulation on this S100 card. I have jumpered V in and V out here on the 7805 regulator, and that's why I can power it from the plus 5 volts off of the RC 2014 here. So that is something I did to allow me to power it directly from 5 volts. If this was being put back into an S100 machine, that jumper would need to be removed, or the 8 or 9 volts, whatever that voltage rail is that comes in would, of course, most likely fry the parts. So just so that's called out, that's why you see that strap right there. I'm going to wrap this video up here. There's no reason to go any further in this video, and I'm going to get set up to program some actual parts, and we'll pick that up in the next video. By actual parts, I mean actual ROMs for my MST-80.